Well, good morning, good afternoon, and good evening, folks, wherever you're joining us from today. Welcome to Simulation Hub's latest webinar on how to assess IAQ and thermal comfort of buildings at the design stage test using AHC 2023. Today, we are going to introduce two wonderful speakers, and let me kind of change my slide a little bit so I can bring these gentlemen up. Robert Bean is the director of healthyheating.com and a founder of Indoor Climate Consultants Incorporated. He's a retired engineering technology professional who specialized in the design of indoor environments and high-performance building systems. Mr. Bean is an ASHRAE, I want to make sure I get those all in there, fellow, and an ASHRAE Distinguished Lecturer, recipient of the Lou Flag Award, Distinguished Service Award, and instructor for the ASHRAE Learning Institute. You got those awards in there, so you must be trying to get rid of you, Robert.
That's right.
And then
Exactly.
also Praveen is the product manager of Simulation Hub, the flagship CFD platform of CC Tech. With more than 15 years of strong domain experience in CFD, he has also developed a flavor for user experience. But before we begin the webinar, let me complete some housekeeping items for you. We are recording this webinar and it will be available to you for your future reference on our YouTube channel, as well as on Simulation Hub's website. And we'll put that URL up or in chat, I'm sure. I request everyone to keep your mics on mute during the presentation. You never know when the smoke alarm or whatever is going to go off, or the cat or the dog. Meanwhile, if you have any queries, please feel free to post those in the chat box, and we're going to monitor that. And at the end, we'll have a really nice Q&A session. Let's go over the agenda very quickly. Robert is going to first help us understand how thermal comfort and indoor air quality play important roles in human well-being. Praveen is then going to walk us through how thermal comfort and indoor air quality can be assessed using our latest app, AHC 2023. We'll have the Q&A session at the end to answer your questions, any questions from the audience. So without further delay, Robert, I'm going to hand the mic to you. It's all yours.
Thank you so much for having me speak about something that I'm very passionate about that plays a big role in building. So you should be seeing the first screen. And I just, have been very fortunate in my career to travel around the world and get to visit some awesome architecture. And it always amazes me that it doesn't matter what country or what city I'm in, that when you look at buildings, that oftentimes the design community, the property development community seems to forget that the reason why the buildings exist in the first place is because of people. And there is obviously a strong voice worldwide, globally, to conserve energy and to be efficient with energy. And ultimately, when we think about architecture and buildings and people in buildings, every time energy is converted from one form or another, it's because somebody's unhappy with the environment. They're trying to get out of a state of discomfort to be in comfort. And that, of course, is what drives heating systems and cooling systems. And then, of course, the idea that architecture ought to be the first solution in fixing these problems, but oftentimes it isn't. So it's important that we understand occupants, or why buildings exist. And it's important that when we understand the term indoor environmental quality, that we're not specifically talking about just air quality, but in fact, we're talking about all of the sensory systems of the human body. So the ways that we sense and perceive and judge the indoor spaces is based with all of our sensory systems for odor, sound, light, thermal comfort. All of these things are very, very important. So when we talk these environmental systems, we have to understand that they can be stressed. And we see extreme cases where someone, for example, might be in an office space with other individuals fighting and arguing over thermostat setting or lighting, the shading, the blinds. Sounds is another one that drives people crazy. So all of these sensory systems that we have can get stressed out. And that is really the study of, the differences between homeostasia and allostasia. So homeostatic states where your body and mind aren't stressed out, to where we actually want to exercise. We don't want environments to be so stale that they're boring. So as indoor environmental designers, we're trying to always find a balance between a really good environment, but not being so boring, but not have environments that are so severe that they cause us stress and worry. And we do know from studies from various organizations around the world that when you look at buildings and the cost of buildings, not only the cost to build them, but to operate them and maintain them, that relative to these costs, the people cost is actually the highest of all. It's the salaries and the benefits and the time off due to vacations or sicknesses or whatever it is. So really, if we can improve productivity in buildings, even by a small amount, 2-3%, by creating better environments, it makes the energy bills look like belly button lint. It's so insignificant. That's not to say that energy is not important, but we know that the people costs and productivity costs and learning costs are far more important and have far more importance in society. So I want to talk a little bit about air quality. Its importance, and we need to understand that really what air is, it isn't in fact a conveyor belt. It moves throughout the space, either naturally driven or through mechanical means, but it does move, and because of that movement, it actually moves other things with it. So when we talk about the air that we breathe, it's just not air for the sake of air quality, but there's contaminants and pollutants and toxicants that can also be in the air. So it moves these around. And as we inhale, there's many functions that take place during the inhalation process, from conditioning the air with temperature through your nasal passages. Of course, it stimulates the olfactory nerves in terms of smelling. There's also cilia and mucosis that does filtering as well. And so this taking air in and taking air out serves not only the process of providing the body with oxygen, but also treats it as well from an air quality perspective. And where we get concerned has to do with the deeper part of the lungs when we get into the alveoli. And this is these small little sacs where it's basically a single cell thickness, where the air that we breathe in and the oxygen moves from the outside world, which is the inside of our lungs, into the inside world, which is our blood. And these tiny little sacs, these alveoli, there's anywhere between 300 and 500 million of these in your lungs. And someone at one point had estimated that if you take the surface area of these and spread them out, they would cover the area of a tennis court. That's how thin they are. So it's pretty amazing to think of it from that perspective. So when we inhale, we have vapor pressures, gas pressures, that move the molecules across the cell of the alveoli into the blood system. But when we exhale, of course, we're exhaling carbon dioxide. And this, of course, is one of the metrics that we measure indoors. And we can tell what the dilution rate is by looking at numbers, CO2 numbers, whether they're within acceptable measures or not. And that can tell us a little bit about what we call the rebreathe rate. How many breaths are you taking that actually somebody else exhaled now becomes your inhalation breath. And we also know, though, that when these process takes place, that some particles get caught inside the alveoli, and that's what these macrophages are all about. So when we talk about things like asbestos, these particles can't pass through the membrane. They end up getting caught in the alveoli, and the body responds by sending out these macrophages, which are like Pac-Man for anybody that's old enough and knows what that's all about. And that's what actually end up developing the scar tissue that leads to the dangers associated with asbestos, but also other airborne particles. Now, those particles that end up passing across the cellular membrane of the alveoli can end up in the blood system. And some things are of a benefit, some things aren't. And the things that aren't of benefit to the human body, the body responds by releasing white blood cells. And these white blood cells will search out these foreign matters that don't belong and try to to neutralize them. And once have been neutralized, they pass through the cleaning mechanisms of the human body, and that's your spleen, liver, and kidneys. And you can think about them as sort of the green, blue, and black recycling bins that we have in some societies. And so their whole process is to clean the blood, sort of a chemistry set, if you will, for some of the organs to give it, its original characteristics. And for those products that aren't there but can be eliminated, they get eliminated out through the urinary systems. So the body will take care of that. But when we get into bad things in the environment that don't belong, then what can happen is that these can accumulate in the body. And that is the study of what we call the exposome, looking at how the body responds to a lifetime of exposures where the organs can't deal with it. So it's important that we understand airflow, and it's important that we understand the characteristics of the airflow, and to make sure that when we have air moving around, that we see it as a conveyor belt, and that if there's things on that conveyor belt that are not good for us, that we ought to understand them and try to control them through other means, filtration, ventilation, dilution, these types of things. So then I want to talk a little bit about thermal comfort. And of course, thermal comfort is another one that's very fascinating. Regardless of your beliefs of how our species ended up on the planet, doesn't matter where you are, whether you're in Mumbai or Fairbanks, Alaska, or Sarasota, Florida, the human body has an array of sensors, and these sensors are distributed not in a homogeneous way around the body, but in various locations that oftentimes receive more exposure to the indoor or outdoor and indoor environment. So it's pretty interesting to note that it doesn't matter who you are or where you are in this world, the greater number of sensors are in our areas that get exposed more, like in the head, the back of the neck, the hands, and the feet. And these sensors, they send information into your central nervous system. They synapse into the central nervous system, and they end up in two places in your brain, the hypothalamus and the thalamus. And so the body actually responds in a really magnificent way to changes in temperature, and again is picked up by the thermal receptors in your skin. And that information is sent, as I said, synapse into your central nervous system as a signal, where it's collected in the thalamus, which is like a grand central control station, if you will, and it sends information to the parts of your brain where you have conscious thoughts, like I'm hot and I'm cold. But it also sends information to the hypothalamus. And when the hypothalamus receives those neurological signals, it does a comparison to what it's supposed to be when it's happy. And if it's not happy, then it makes some decisions. And at the same time that it's receiving that neurological signal, it's also receiving the chemical signals, T3 and T4 hormones, which are associated with metabolic rates. And when those values deviate from the setting of happy, then the hypothalamus makes a decision. Listen, we're not in a comfortable state, we need to respond. So if it's in a cold state, we're actually cooling, feeling cold, then it sends out a hormone called a thyroid releasing hormone. And it sends that hormone to the pituitary gland. And so the pituitary gland basically takes that chemical handshake and says, all right, well, I'm being told that the body's not in a happy state right now, and we need to do something about it. So then it sends another hormone called a thyroid stimulating hormone, TSH. And that thyroid stimulating hormone is received by the thyroid, again, as a chemical handshake. And the thyroid then says, okay, well, we need to start producing T3 and T4 hormones and release that into the bloodstream. And then those hormones travel out into your system looking for receptor cells that are associated with metabolic processes. So when you start to get cold, how the body responds is it starts to constrict blood vessels. It actually tries to retain its heat. So it stops sending as much blood flow to the skin, sends it to more vital organs to keep it warm. And when you overheat, need to get rid of energy, then those blood vessels, they open up, they dilate. And by opening up the blood vessels and sending more blood to the skin, then you increase the surface temperature of the skin. And then, of course, you increase the delta T between the skin and the environment. So you promote radiant transfer. But also you see the opening of sweat pores. So you end up with evaporative cooling and radiant cooling. And then you have convective as well. So that's all done through the neurological systems, your endocrine systems, and your neurological systems. And we can see that using positron emission tomography or PET scans. We can actually see within the brain what happens to the body as it responds to cooling or heating of the skin. And that whole study of thermal comfort, how people respond to it, has been the work of ASHRAE, and which was that large acronym that Grant read out. So ASHRAE have been doing study and research work with colleagues around the world for many, many years. And this particular standard was written in 1966. And it defines, much like cake. Really, it describes the ingredients of the cake that are necessary for people to sense and perceive the environment to be thermally comfortable. And one of the authors or the contributors to that standard was a professor by the name of Fanger. And Olaf Fanger, really, that was his one of his lifelong works, was understanding people within spaces and how do spaces affect the sensation and the perception, and how does that influence productivity and learning and this type of stuff. And he basically said, well, if we get everything right, then we know within reasonable predictions that the architecture is right, the enclosure is right, the interior design is right, the mechanical systems are right. And he came up with this scale, the predicted mean vote and the percentage of people dissatisfied. But he also understood that if we don't get these metrics right, architecture is bad, enclosure is bad, the interior is bad, the mechanical electrical systems are bad, that we have a higher probability of people being uncomfortable. So we can use this as designers, but now with these software tools, of course, we can model them. So one of the messages about, when we look at building codes is that codes in of themselves do not address thermal comfort. We know almost anywhere in the world that when we look at building codes that there's some kind of objective to maintain some kind of indoor, and it's oftentimes it's referred to as air temperature, and we're going to find out that that's a lame metric for thermal comfort. And so that if you can take air out of a space, put air in a space and maintain some number, 72 degrees or 22 degrees Celsius or 68 Fahrenheit or 20 degrees C, something like that, that you'll meet the requirements of the building code. But when you understand people, which is what the ASHRAE standard is all about, that you'll begin to understand that it's far more complex, but also very elegant. And we've experienced this. Every one of us have experienced the different forms of energy moving through a building, on a building. And it starts with the sun. Every time in the morning, the sun shows up and it starts to dump a bunch of radiation onto the building. And we call that radiation shortwave energy, very high intensity. And it will then be absorbed by the solid surfaces of the building, and that gets conducted through, and then of course gets released as long wave radiation. So we have long wave radiation in the space. We have windows that allow shortwave radiation to come through the space, and that shortwave radiation is then absorbed by walls and floors, and then it gets absorbed and raises the temperature, and of course then it gets re-radiated as long wave. So we have shortwave and long wave radiation in the space. We have temperature stratification due to buoyancies. We have draft also due to buoyancies. So cold air coming across the floor or warm air at the ceiling, and that causes temperature differences between the ankles and the head. And we have changes in humidity. As you walk within a space, the humidity changes. That's why they call it relative. And we have people wearing different clothing and doing different things. And so we have all of these ingredients that work within a space. And when we understand architecture and enclosure and interior design mechanical systems, then we can design for these metrics as opposed to just taking some arbitrary number and calling it a representative thermal comfort, which is what building codes do when they say, well, if you can maintain 72 degrees Fahrenheit, you're good, or 66 or 22, whatever the number is. But the reality is that the human body, roughly 60% of its sensible heat transfer is done via radiation. So codes that reference air temperatures don't reference comfort. That's not impossible. It's not possible. They've missed almost 10 or 11 other metrics that we look at when it comes to designing spaces that are in compliance with ASHRAE 55. And that, of course, is the further conclusion on that, is that when engineers and architects and design professionals do load calculations, those load calculations aren't thermal comfort calculations. You have to extend those calculations into a compliance calculation. And so that's really important as well. So when we look at codes, when we look at load calculations, and when we look at HVAC design, these three are not comfort calculations. You have to look at the architecture. You have to look at the enclosure design. You have to look at the interior finishes. Color plays a big role in absorbing or reflecting energy. It has a big role in air quality as well in terms of releasing gases and particles, all of these things. So they're all integrated and you have to understand them. And that's why when we look at buildings and we do assessments of buildings, why these software tools are really important, because we need to understand not only in terms of the air movement through a space, but also the enclosure characteristics, the temperatures that we have, the humidity they have, the air velocity that we have, because those characteristics ultimately will influence people. And of course, then their sensation is affected and then their perception. So I want to just take a few seconds here and we'll finish up and talking about the importance of modeling these spaces, because when you look at architecture anywhere in the world, and you look at a failure to be in compliance with standards, that there's a lot of square footages, square meters in buildings that are unoccupied because people can't get close to the exterior because of noise, lighting, sound, thermal comfort, all of these types of things. So we have a lot of area in buildings that we can't use because of poor indoor environmental quality. And if you think about the cost of that, not only the economic cost to build those spaces, but the resource cost that we, rape and pillage Mother Earth to extract materials to build these spaces that we can't use, that's absolutely insane. And so if you think about just one example, one office building that might have whatever, a $200 a square foot construction cost. Well, if that area, roughly 20% or 30% is unusable, well, the construction cost for the usable area goes much higher than $200 a square foot, right? So there's this penalty, huge economic penalty to build spaces that we can't occupy. Well, that's just one office. And you think about one office and one office tower on one city block where there's literally thousands of offices that are like that. And then you take how many city blocks in one city that might have these conditions, and how many cities in one state or one province, and how many of those in one country, and how many countries are like that. And you begin to understand just how big a problem having unusable spaces is around the world from a cost and energy point of view. It's absolutely crazy. So we need to correct that. And one of the ways of doing that is to use modeling tools to help architects and the clients and the engineers and the developers understand how buildings have an integrated, intimate role with the indoor environment, and how by changing architecture and then changing the enclosure design and interior mechanical systems, that we can improve the indoor environmental quality throughout the entire space, so that all the square footage that we build, from looking at it from an economic cost and also raw material costs, it gets utilized to its fullest potential. And so I started my talk this morning talking about people and buildings. And I would just really encourage everybody that's listening today that we understand why we build buildings in the first place. It's for people. It's all about the occupants. And we need to understand how the occupants have an intimate relationship with the indoor environment through the sensory systems that we have. And then we develop perceptions, and those perceptions ultimately can influence not only our state of stress, but also our learning abilities and our productivity. So that is my message that I have for today. And I want to thank everybody for the opportunity to present this information, and look forward to listening further to the seminar and learn a little bit about the software tools. So thank you.
Fascinating stuff, Robert. Thank you so much for providing invaluable insights to our audience about thermal comfort, indoor air quality, all that stuff. It's fascinating how many times you've been to a building and it's just uncomfortable and you can't figure out why. Here's all this money being spent. So anyhow, as Robert said, achieving those optimal levels of these parameters is complex, and software tools like AHC 2023 can help HVAC professionals. And having established this fact, I'm going to hand over the mic to Praveen so we can know more about the AHC 2023 and how it helps assess the building comfort, thermal comfort, and IAQ of the building at the design stage before all that money gets spent. Praveen, it's all yours.
Thanks, Grant, and thank you, Robert, for enlightening us with thought-provoking speech. So it made it easier for me. You have set the right context, so from here it'll become easy for me to take it forward.
Very good.
That was about how important it is to assess or know thermal comfort and indoor air quality of the buildings. Now the time is, we'll discuss about how to assess these parameters. So there are ASHRAE and ISO standards which have defined how to assess thermal comfort and indoor air quality via number of indices. So when I talk about indices, there are like comfort and air quality indices. So to name a few, it is like, as Robert mentioned, explained about predicted mean vote, PMV, and PPD, draft rating, effective draft temperature, ADPI, and there are local discomfort parameters that can collectively guide you whether the building is able to provide occupant thermal comfort or not. And when I talk about quality, air quality indices, then AQI, air quality index. So let's pick one of this, which is PMV, and then let's see what it takes to calculate or evaluate PMV. So as Robert mentioned, Professor Fangio's comfort model help us to calculate the predicted mean load. So what it takes is like you need to provide two set of inputs. One is the personal factors, where what is the activity level or metabolic rate and clothing insulation the occupant is wearing. And the other one is environmental factors, which is the temperature, humidity, mean radiant temperature, and the air velocity. So once you have these inputs, there is a set of equations which can give you the PMV value, and you can map it with this scale, thermal sensation scale, and you can understand where you stand, whether you fall in the comfort zone or the warmer side or the cooler side. So we saw the predicted mean load or any comfort index is a function of these four parameters. That was for PMV, but what about other comfort indices and air quality indices? So the PPD, effective draft, temperature, draft rating, ADPI, and everything you see, all of these comfort indices and air quality indices are function of these 5 or 6 parameters, which are environmental factors. So which is air temperature, humidity, velocity, MRT, and contaminant concentration. So now our job becomes easier. Once we have these parameters measured, we can evaluate or assess any comfort indices. So what are the different methods available for us to measure these parameters? So one is can do physical measurements on the site, and other option is to simulate or use CFD, computational fluid dynamics simulations, to predict or evaluate these parameters. So let's see what are the pros and cons of both these methods. So in the physical measurement, it is, yes, the pro is like the advantage is you're measuring the comfort on the real setup, but that has the other side as well. It is possible only after construction. It is not possible to do this at the design stage. Only after construction and installation is done. So that is the downside of it. It provides you with limited flow insights, because wherever you install or measure or install your probe, only at those locations you get this detail. You do not have the complete picture of the space. So it limits you to by the time you realize you're lacking or you're failing to meet comfort criteria, it's too late, because it's at the construction stage. Now it is difficult. It causes delay and high cost to make any design changes at this point. So on the other hand, if we say CFD simulations, yes, it can help you to predict comfort at the design stage well before commissioning or installing is done. So you get more detailed flow insights of every point in the space. You can visualize the hot pockets, cold pockets. So all those details, flow separation, where there is a recirculation is happening. So all those details you can get from CFD simulations. But the conventional CFD simulations also has some challenges. So it demands CFD expertise to use or operate these tools, softwares. And it also comes up with, it demands in-house high power computing setup. And the software cost and computer resources are, added challenges, which makes it very challenging or not so motivating for the HVAC professionals or the HVAC community to leverage this wonderful technology. So now that brings it. So at Simulation Hub, we wanted to address these challenges, and with this vision to take this wonderful technology and democratize and take it to the hands of every HVAC designer and professionals, IAQ consultants. So with this vision, we built Autonomous HVAC CFD. Okay. So what it is a cloud-based upfront CFD application built for HVAC designers and IAQ consultants. So it is backed up by a lot of technology in the background, like Autodesk Forge, OpenFOAM solvers, and AWS Cloud Platform. So what it does is it takes 4 design inputs: the architectural design, the enclosure design. The enclosure design includes, the properties, the color, tint of the glass. So all this comes into enclosure design. And the interior design, which includes the people itself, along with the furnitures and other heat appliances that will add heat load or some CO2 sources maybe in the space. And the 4th is the mechanical design, the complete HVAC design. So once you have these 4 inputs to AHC, so what it does is it provides you with parameters to assess indoor air quality and thermal comfort of the given building space. So when I say indoor air quality and thermal comfort, so it provides you with, as I mentioned earlier in the speech. So these are the 4 environmental factors, 4 or 5 environmental factors: humidity, temperature, airflow, draft, and radiant temperature, and using which the data is processed to calculate the ASHRAE 55, PMV, and much more like PPD. So all those comfort indices can be calculated and provided you in a easily understandable or interpretable format. So we also this app also provides CO2 concentration cloud. So you can view and understand which are the zones which are having healthy air and where the air is above acceptable indoor air quality. Okay, so moving on, why we should consider using AHC for your indoor air quality and thermal comfort assessment. Thing is, it is autonomous CFD. So when I say autonomous, it is a mix of intelligence plus automation. So the app does all the heavy lifting of the CFD simulations. So it starts from CAD cleanup, meshing, and solving. So all these processes are taken care by the algorithm. So the user doesn't need any CFD knowledge to use the app. And secondly, the simulations are performed on cloud platform. So which means all the simulations, all the space, all these simulations are performed parallelly on cloud. It doesn't demand any of your local computers for this simulation purpose. And you can imagine, because it's a web app and SaaS product, there are no limitations of how many projects you can run parallelly and how many design configurations you want to run and compare them. So all the results will be ready at the same time. So all this CAD cleanup, meshing, and solving all are CFD microservices built on Simulation Hub platform. Okay. So what are the new features that we have added in AHC 2023 release? So last year, we released the early access of this app, and we got to connect with a lot of people working in this domain. And based on the upvotes of feature requests, and after understanding their requirement in the market, so we came up with this adding up CO2 concentration feature. So where you can visualize what are the zones where if the indoor air quality is in acceptable or healthy or hazardous zone. So that you can visualize here. And along with that, we have improved the MRT calculations, mean radiant temperature calculations. Earlier, it was a single approximation, which was average of all the surface temperature. But we were not happy with that. We wanted to give you more accurate results. So we improved those calculations, and now you can see the regions where the mean radiant temperature is more and less. So this distribution is perfectly calculated with this improved logic. And we have also added support for inverter and non-inverter ACs. So where you can specify and select, there is a library provided, and users can just pick and place the AC units in the design space and specify what is the tonnage of the AC, whether it is an inverter or non-inverter type. So based on these selections, the the background calculations are made differently. So another feature which was in very demand was like adding outdoor air mixing in the app. So the CAV, VAV, or even for that matter, some cassettes which provide outdoor fresh air addition. So those can be modeled or used accurately. So now we have included psychrometric calculations, so which calculates your supply air conditions, temperature and humidity more accurately based on the return air and the ratio of mixing that happens with the outdoor air. And this feature was in very more demand, and we have brought that, which is infiltration. So the infiltration is the air, outdoor air entering, untreated outdoor air entering into the space through the leakages of windows, doors in the on the exposed walls. So that feature we have brought in, and this infiltration does add load on the HVAC system, and in fact, it will affect the thermal comfort and indoor air quality. So that feature it's adding more value to the app now. And we have also added much more occupant activity levels and things. Okay, so now it is time to see the app working in action. So let me walk you through a quick demo of the app. Okay, so this is a web app, so you can directly, there is no installation required. You directly log in to simulationhub.com and start creating projects. So for the first time, you have to sign up and create your account in Simulation Hub website, and there you go. So you end up in the dashboard, project dashboard. So you can have a look at all the projects and create new projects. Give a proper name and select the type of analysis you want to do. And you can provide certain details of the building space and set the material properties available from the material library, ready to use a material library. And you give the site location, and the app takes the weather conditions from the nearest weather stations available based on the site location. So you get to select the building orientation, and you are ready to create the building using the SketchUp tool. So you can place windows on the exposed walls, and from this BIM component library, you can place plug and place the furniture or the seating layouts along with the occupants. And their metabolic rate and the clothing, everything you have control over that. And here you're ready to create the new airside systems, and you get to provide the infiltration rate, and there is a BIM component library for selecting diffusers and AC units. So you can place the supply and return. So you can create multiple airside systems. Design configurations, and then you can simulate them, compare it. So yeah, so the next step is to create design configuration, where you get to select what is the type of HVAC system it is. So is it a VAV system or CAV or multi-zones? So you get to create different zonings and provide certain inputs related to the system, HVAC system. So now you're ready to create different weather scenarios and occupant density scenarios. So the winter, summer, and extreme occupancy. So once you have all these things ready, you can have start the simulations of all the year-round simulations and all the possible configurations you want to compare and simulate. So all these simulations are run on cloud platform, and you can view the progress. Once the simulation is completed, you'll get a notification, and yeah, you can view the results in the web browser. So we have easily understandable thermal emojis, which give you the sense of what is the thermal sensation of those occupants in the space. So moving ahead, so there are, other than thermal comfort, we have indoor air quality and other tools, post-processing tools like surface plots and cut sections, flow lines. So that will help you to visualize and investigate where there is a issue, the indoor air quality or comfort issue is there. So you can get to the root cause of the problem and try to rectify it. So what you're seeing right now is the indoor air quality CO2 concentration cloud. So using which you can identify what are the hazardous or healthy air zones, and there are other tools like more and more cut sections where you can view and identify what are the hotspots and cold pockets in the space. So mean reading temperature, velocity, draft ratings, all those indices which are discussed in the previous slides. So those are available in the app. So that's Autonomous HVAC CFD. Okay. So the next thing is because with great powers comes great responsibilities, right? Like, so we have taken the responsibility of setting up all the CFD processes and making it autonomous. So the responsibility lies on us. So we have to validate the app and give you more accurate. We need to fine tune the setup to provide a more accurate results for it. So we have validated this app with a bunch of literatures or experimental data which are available in the literature. So I'll go through each and every, I'll go through a few of the validation studies we conducted. So this one was experimental data conducted by GPay and team. And there was a displacement ventilation and with a single person seated, and it's a mannequin which is simulated. And here you can observe the stratification in the temperature contours and also the CO2 concentration levels. And when we compared this with, when I plotted this like with the CFD versus experimental, the CFD results closely follow the trend of the experimental data, both in temperature and also in the CO2. So another case what we done is, this is in our office, CCTech office, conference room, where I'm delivering the webinar right now. So that is a closed space, and we often feel, we wanted to, we were excited when we developed this app. We wanted to, measure the CO2 level inside, and we wanted to compare it with the AHC app, what it provides. So we installed certain sensors at the breathing level of occupants at different positions, and one at the supply of the AC. And with that, we did perform a few iterations, few experiments, and I'm sharing one of such experiments, one of the conditions. So where you can see the temperatures, we are able to predict in the range of about 95% accurate, and in relative humidity, we are pretty much above 90 and mostly above 95% accurate. And CO2 concentration, we are in the average of 85% of accuracy. So this is pretty good for the upfront CFD app. So adding to the validation case, there is one more case which is called the benchmark test computer simulated person. It's a Comfortina model. It's well known as Comfortina model. So there, the team, Nielsen and team has performed this experimental setup, experimental data, and we have compared our AHC results with the experimental data, and it is pretty much following the trend and closely following the experimental data. So in right immediately behind the occupant as well as near the occupants. So with this, I'm jumping to the case studies, different case studies, interesting case studies that we have performed using the app. So here we have performed, we have taken a office space, small office space, and compared the results of displacement versus mixing ventilation. So displacement ventilation, the supply is at the floor level and the exhaust is at the ceiling. And for the mixing, it's both supply and return are at the ceiling level. So here you can see the stratification of temperature, and this displacement ventilation system, it requires very less, or it can perform good even at the higher supply temperature compared to the 13 degrees Celsius for mixing ventilation. So the energy savings is much that is clearly visible, and also because of the setup of the flow, it carries away the contaminants or CO2 towards the exit. So you can clearly see the average CO2 concentration of displacement is much lower than the mixing. So this means it requires only less amount of outdoor air to provide the same level of indoor air quality as that of mixing. And here is another case study which is showing the effect of cold air draft on the occupants. So here you can see some low temperature zones, and where the PMV is also suggesting the PMV is going in the negative side, which is too cold side. So that is because there is a cold draft directly falling on the occupant. So that you can capture, and you can compare even for large spaces. You can compare multiple design configurations, whether it is a swirl diffuser or a linear wall mount diffuser, and then you can compare the hot and cold pockets of this for the same project, and then you can make informed design decisions to which one you should go for. So here is another interesting case where what is the impact of window glass tint and how it is going to make the system work in the favor of occupant comfort. So when the glass is tinted, the system is able to provide comfort almost like every occupant. Okay, so we are nearing the end of the session. So this is we have various subscription models for which is suitable for individual consultants or consulting firms or large enterprises, large organization, architecture firms. So they can opt for whatever plan that suits their need. So you can also start with a free trial, which comes with 90 days trial, and you get 5,000 credits, which means you can simulate up to 5,000 square feet of build space to get the idea, to understand what the app does, how it works. Okay, so we come to the end of the session. Yes, Grant.
Yeah, thank you, Praveen. That's amazing software, and thanks for the fantastic app demo and an overview. The ACH 2023 is definitely going to empower designers and system design, freeing them up to expeditiously create innovative, efficient, and sustainable solutions, and evaluate the designs to ensure that indoor air spaces provide the best comfort possible. So if there's any questions, I have a couple to ask, but if you've had the opportunity to be in chat and would like to put a question through to Praveen, and I think Robert is still hanging around. He hasn't retired fully yet. So I'll go ahead and start with a question that I had, Praveen. Does the software work over the entire building design or just a room?
Okay, this software works for the entire building space, which is supplied by the same air handling unit. So the complete entire space.
Okay. Does it take air balance into account, and or then does it suggest how to balance the space or a building?
It does not exactly suggest the air balance, but it does take care of air balance into account. So in the input, you get to select what is the supply flow rate and what is the return. So with that, yes, this is kind of that is the input required for the app.
Okay. And I had my question and also another one that are right in line. I noticed you designing a room. Can it input, like if I've already got a CAD design or whatever, will it pull those data points in so I don't have to redesign the space again?
Okay, so we are working on integrating the importing CAD models or building information models from different software. But right now we are providing with the floor plan sketcher using which you can create the design. But we are working on the Revit integration or other file formats that can be imported. You can expect it in this quarter or next one. Soon.
Yeah, I think there is one more question, Praveen, from one of the attendee. All these actions were performed on ANSYS CFD or any other software? They want to know how these simulations were performed.
Okay. So we are using OpenFOAM solver, which is well validated, and even the method is validated as I shown in the validation study. So in the background, we use OpenFOAM solver, not the ANSYS CFD or anything. But other than the experimental data, we have also compared our results with commercially available software as well. So we are in par with those results as well.
So just to elaborate further, so this is not using ANSYS CFD. This is our own algorithm that are built on open source technology, or that is called as OpenFOAM. And so this is a different software, and ANSYS is one of the software that, in a sense, we compete. And yeah, so I think there is one more question about, can we get a noise level and air change rate through the software?
Air change rate, yes, not the noise level right now. So we have started. Initially, we started with thermal comfort, and then we moved into indoor air quality, and slowly we will, in the future, we'll go cover the indoor environment quality, IAQ. So noise and visual as well. So that is in the future roadmap, but right now, yeah, it's only indoor air quality. But air change rate, yes, that we provide. So,
yeah. I have one question for Robert. I was listening to his conversation, and how it impacts our body and every breath that we go through our things. And it is such an important area, affecting things. But still, we see a lot of people are not aware about it, or even they know that it affects. People don't work on these things. Why there is so much of ignorance, I would say, in our community about designing really healthy buildings?
Yeah, there's a lot of ignorance. Illiteracy is really what it comes down to. We have mass scale illiteracy when it comes to indoor environmental quality, and the problems are complex, or the reasons are complex. But I would say one of the key areas has to do with building codes and people's assumption that building codes are there to provide good indoor environmental quality, when in fact they're not. Most building codes are written to reduce the probability of risk that somebody will become ill due to air quality or thermal comfort or exposure to moisture, these types of things. So what happens in practice is that the minimum requirements of building codes become the maximum in industry. That's a principle that applies in many, many fields. The minimums become maximum. And until we have industry understand that building codes are minimum and not maximum, that we will, and if the economics continue to drive in terms of competitiveness, drive building design and building construction to the lowest denominator, we will have a problem. But these things are changing though, because we have enough good buildings around the world now. You know, if you think of in terms of a barn and horses, the thoroughbred buildings that we have available are really demonstrating that we can build good buildings and we can have great indoor environments and they can be energy efficient and they can conserve energy, and that these buildings now become sort of a flagship for architecture around the world, and that buildings that aren't designed to meet those benchmarks really show up in post-occupancy evaluations where the occupants aren't happy. You know, when you look at the data points for sound, light, thermal, odor, vibration, these types of things, the failure rate that we have. Well, if you're a large corporation and you're considering the environment for your people, and you have a choice between a building that has good indoor environmental metrics and one that doesn't, and if you're acutely aware of the intimacy that people have in terms of productivity, learning, all of these things, you'll pick the better building. And we're starting to see that. And we're starting to see really large corporations who are building their flagship buildings, you know, that consider the human factor in design. That, in fact, is the driving force for the building, rather than looking at it purely from an artistic point down. Typical, when you look at traditional architectural processes where the client engages an architect, they come up with a creative design, and then it gets, you know, floated down to all the design professionals. These buildings that are built around human factors, they start with human physiology and psychology as a driving force. So they look at surface temperatures, and they look at the materials of construction, and they look at outgassing and particle, you know, development and sound and all of these things. And so that actually drives the design. Right. And I know when we were practicing, just to give you an idea, this whole change, you know, that our own practice went through happened about 20 years ago, when we realized that we were designing the codes and we could still have people complain about the environment. And it wasn't until we learned about human physiology and psychology and started to incorporate that in our design that the number of complaints went away almost within a year. You know, a year of releasing drawings for construction, the feedback that we got was we had no idea that buildings could be so comfortable.
Right. No, I think this is really a great input, because a lot of people in our industry just rely on hit load calculations, sizing, and then they say that's it. That will make sure everything will be comfortable, everything will be good quality.
Yeah, and we know that's not the case.
Right.
You know? Yeah, so that's a good question, you know, why we still have this problem. So codes is definitely one of the other problems. And the second one is that in many parts of the world, the requirement for professional development is based on the size of the buildings. In other words, small buildings don't require professional engineers or interior designers or architects, for that matter. Anybody could build a building if it's, say, under 20,000 square foot single level building. And, you know, and because of that, the design team oftentimes are individuals that have no secondary education. They don't understand the relationship between occupants. All they know is they have to meet the requirements of the code. So I think one of the other things that needs to change is we need to make indoor environmental quality a primary design consideration in all design for all buildings, because ultimately we're dealing with people, and it doesn't matter whether it's a 300 square meter building or a 3 million square meter building. Like, it doesn't matter. It's still the person.
Right. I think there is some more question coming. We will take, I guess, last question, Grant, and close the session, I guess.
Sure. Does the application provide any certification like ASHRAE or any other code having the requirement of the simulation?
I guess I might be the right person to answer that question. Okay, so right now what we do is we provide all the detail that is required to, you know, you to adhere to the ASHRAE 55 standards or the ASHRAE other standards. We plan to generate a PDF report in which there will be a lot more detail that you will take, and then you can go for a compliance and others. So that is the way we plan to do. Right now we are just generating a data, but we are not generating a certificate. Right.
Okay.
Thank you.
Thank you for that.
Yeah. I'd just like to add
Thank
on to
you
that, you know,
Robert.
that
Oh,
Yeah,
Yeah,
please,
I'd
Robert.
just like to add on to that, that ultimately it's the design professional that has to make sure that the space is compliant with the standards. It's not the program's job to do that. That is actually the design professional. What these design tools do so well is that they give the design team the ability to visualize the potential problems in the space.
Yeah.
You know, the competent designer will have an understanding of thermodynamics and fluid flow and, you know, how these spaces should be designed. What the tools do so elegantly is provide that visualization and also the output and whether you're going to be in compliant with the standard or not. So I think it's great that these tools and your tool in particular can do these types of things, and that you'll be able to point out through the report that you're talking about, you know, these are the areas that you're compliant in, and these areas that you should take a look at that are causing maybe a non-compliance issue. And that might only be one area of a space. Like it could be a south west facing space that needs to change its glazing from double pane to triple pane, you know, and changing the coatings, you know. And I think that's one of the huge, powerful elements of these tools, is allows you to pinpoint with reasonable accuracy what things need to get changed so that you can be in compliant.
Right.
Yeah. So I think that's awesome.
Thank you.
Very good. Well, thanks again, Robert, for helping us define all that stuff. Thank you to Praveen for the great demo, and for Sandeep for jumping in there with some answers that we didn't have otherwise. And thank you everyone that is on the webinar. Thank you for attending. And for those of you listening, we hope you find value. I hope we provided you with some valuable insights on how to assess indoor air quality and thermal comfort in the initial design phase using the Autonomous HVAC CFD. Now, if you sign up now, you get free credits worth $500 for 90 days. You can explore Autonomous HVAC CFD application and evaluate HVAC designs for indoor air quality and estimate thermal comfort up to a space of 5,000 square feet. And as I mentioned earlier, we are recording this webinar, and it'll be available on our website and our YouTube channel. And you'll receive a link for that in your email that you registered with. Thank you very much. And again, stay safe, everyone. We appreciate you attending.